My name is Abhi. This is Really Lab, and this is going to be a quick overview on how to acquire colocalization images using ImageJ or Fiji. So the first thing, of course, you want to do is to download the Fiji software, which is an open source software where you can download the software. Me personally, I will be on a Mac, and so I will be downloading from here. It will take you through a quick upload software installation, and then you'll be able to open Fiji. And from here, you'll be able to do a variety of image analysis. It's important for you to find a proper location for you to store all of your files. I personally included everything in a folder that I've tagged as slew. I also have a drive because sometimes the images can get very large, and so having some kind of external storage source is very useful. We maintain organization by plate, as well as the specific well and treatment. And so you can see these are the 3 images we took at the microscope of well 1 on a plate that was non-treated. And within it, you can see I included all of the images that I acquired from the file. I also keep one large folder that has all of the images, the deconvolved, and the .ims files. Generally, though, we'll be using the deconvolved. However, sometimes the files can corrupt or improperly transfer, and so we will always have the .ims to use as a backup. I also keep all the metadata in a separate folder because it's very unlikely you really use it for anything. But of course, how you organize is all up to you. This is just a method that I personally find most effective. For the sake of demonstration, quickly showcase. Let's do a test file. How to image and acquire images that you can use for a slideshow maybe, and for further analysis from a microscope file. So of course let's call this test file, but let's also add just well 8 30 just in case. So now we have a storage location for our files. We can go ahead and work our way back to our source images and find a file that is correlated to our image, which will be, sorry, do this in the list, and you can see this will be well. Let's do well 8.2, which is the second image in well 8. And we generally work with the deconvolved, and so of course we can drag and drop from our window, or our file window, or conversely we can use file and open, which pulls up this menu, which does the exact same thing. For the sake of this, I will just drag this over here. And now we don't generally have to work with any of these options. You can go ahead and click OK and it should work out. Each of these options are resolutions of the exact same image, and so I will work with the highest resolution image. And so, of course, because it's a large file, it will take a moment to render. So there's nothing much to do, just wait it out. You can go ahead and close off this image file for a moment. And so once we have opened our image, we have a few prerequisite steps before we can start imaging and acquiring workable images. Primarily, we must first ensure that all of our channels are the colors that we want. And so this can be done by using color and the channels tool, which on Mac is Shift-Command-Z. And so I know from my microscope, I know my channels are going to be blue, green, red, and magenta, because that's what I set them as on my microscope. But if I'd like to set this to gray, I can go ahead and do that. Of course, you can always double check later on and see if any of the channels are the wrong color. Next, you should, if you're working with a Z-stack, you need to average the different intensities, so you have a single workable image instead of multiple layers. And this can be done through stacks and Z-project. And so this will take the average intensity of all 51 of these slices to give me a single, more workable image. And then once I have that, I can close the original. And then finally, you can play with the brightness and contrast, which is Shift-Command-C on Mac. Generally, Auto does a pretty good job, so we don't necessarily have to play with it all too much. Yeah, it's a little bit grainy here and there, but should be overall not so bad. And you can play with them as necessary. And so now once you have images that you think work to your requirements, you can go ahead and start acquiring merges and other images. Quick thing to note, though, is that Fiji does have something known as shortcuts. And so these will allow you to speed up your process a lot faster. For example, I have the Z-project keybind coded to Command 0. And so if I were to press that at any point, I can quickly activate that command. And just to quickly add a shortcut, once you click that, it will pull up all available keys that you can attach to a command. And so, for example, if I wanted to, you can also just search this way. If I wanted to make another Z-project keybind, I could do that, click OK, and I will have to restart Fiji in order to have the keybind activate. But also to quickly notice, there are 2 keybinds for Z-project. And so if you do use a shortcut to Z-project and you find it giving you an error, it could be that you have found a shortcut to the wrong command. The Z-project with the 3 dots at the end of it is generally the one that works the best in finding the average intensity. The other one is a different command. Now, of course, I have included split channels to Command 6, stack.gb at Command 8, merge channels at command 7. And these have made my life significantly more easier when working with these kinds of images. And so whether you do that or not is up to you. But from here, you of course want to save, command S, the original image with all 4 of your channels to the location that you have created. So here's our test file, and I'll save this here. And then from here, we can now split the channels. I could press the number 6 right now because I have that key bound, or you can navigate to image, color, and split channels from here. So now you should have 4 images of our 4 channels. They will take a moment to render, I suppose. There they are. And so from here, I can save each one of these images, labeled as what they are. If you are diligent enough to include this inside of your microscope, that is also possible. You don't have to rename them, but I personally do it this way, just so I have all of my antibodies, or the protein of interest, at the very front, so it's easy for me to recognize. So now that we have all of these saved, we can go ahead and start creating various overlapping images, which can be used for colocalization analysis. So for example, I can press the number 7 right now because I have it keybound I have the merge channels window keybound there, or you can instead go to image, color, and merge channels. And so say, for example, we wanted to make an overlap between CD36 and VE Cadron. We can create a composite and make sure to keep your source images so you can continue making more and do not have to reopen the image again. So once you have done this, it has created an image here. And so this actually still has both channels in it, which is why we should take this stack to an RGB. I have this keybound to 8, so I don't have to navigate this window, but it is also image, color, and stacked RGB. So now that I have this, I can go ahead and save it, command S, to the same folder as before, and I can include both of my antibodies, or my proteins of interest. And you can go ahead and do this for any variety of images that you'd like. Generally, though, the idea is to include one of all 4 of your channels overlapping each other, one of CD36 and DAPI combined, one of CD36 and EEA1, one of CD36 and EEA1 keybound to green, which I can show you, and CD36 plus VE Cadron, as well as DAPI, VE Cadron, and EEA1. This can change depending on the experiment that you do, but in general, keeping at least one of all of your channels and then one of your proteins of interest is the gold standard here. And so if you wanted to change the color of one of your images, you can apply a LUT, which overlays a color on top of this image, and you can do a merge just in the way you did it before, and create an image that way. Okay, so say now that you have acquired all of the images that you would like to use, and from here now we can start acquiring some colocalization. So the plugin that we will be using today is known as JACoP, and from here you can install it into your plugins, and it would open up a window like this. It is open source, it is not built into Fiji, which means that you need to search it up. This can be done very simply, JACoP Fiji. Here, you can scroll down, and this would allow you to, it takes you to their GitHub, which you can download their jar, and once you have downloaded it, you can bring it into the files for Fiji. When you've downloaded it, you can go to plugins, and then you just drag and drop the file into here, and then when you restart Fiji, it will show up inside of the menu. As you can see, I should have it in here somewhere. There it is. Right there. And so once you have installed it and restarted Fiji, you should be able to open JACoP and then work with any of the images that you would like to find analysis for. So let's say, for example, we wanted to find colocalization of CD36 and EEA1. We can go ahead and select both of these images and drag them, or of course you can use File and Open. It open in something like this. JACoP will generally auto select which image can be A and B, and depending on what coefficients that you use, it's important to note which ones you do make image A and image B, because, for example, in the Manders coefficient, it finds the amount of image A over image B, and it labels it as exactly image A and image B. It does not use this image name, and so if you do not remember which one is A and B, it will be a struggle to remember which image you are putting over each other to find the number for the coefficient. It's also important so you keep it consistent between every colocalization analysis you do. For example, if you were to accidentally have EEA1 be image A for just one image, it would throw off your coefficient significantly and would lead to errors that would be very hard to diagnose. So for the sake of this experiment, we will only really need Pearson's coefficient and the Manders, M1 and M2. These two are both useful to see if you would like it, as this shows a graph that tests all possible thresholds for the most optimum Pearson's coefficient. It generally isn't too far off from just using the normal Pearson's coefficient. unless there's some error within the images, which would create an outlier, which you could see through the graph, but isn't usually necessary. The cytophotogram is kind of a graphical representation of the Manders in that it plots both of the intensities of each image and determines how accurate to the best fit or linear line their intensities really are. But for the sake of this colocalization, we will only really need the Pearsons and Manders, which requires us to threshold both of the images. And so, as you can see, we are including a lot of background in the CD36, so we can kind of trim it down. Generally, I think that's okay. You can use the arrow keys to adjust as necessary. It is kind of important, though, to keep the threshold value that you want consistent, relatively consistent. I think around 10-ish, 10 to 15 points for parameter value is acceptable, but significant wavering of the threshold value can lead to different results. And so here we can also adjust the threshold. I think that's okay. That's good enough for the analysis that we want to do. And so we can click Analyze, and it will pull up this log window, which has the Pearson's coefficient and the Manders coefficients. And this is why it's important to notate which one is image B and which one is image A, because in the log it notates it as this. And so if you do not know which image is A and which image is B, these numbers will be very hard to interpret. And so from here, we can go ahead and open an Excel sheet. So let's say I want to make another spreadsheet, and we can name it colocalization dot duplicate, because I already have one. But if you do not have a duplicate, or if you do not already have one, you can feel free to name it whatever you like. I will name it on my Mac in here, in this folder that I already have one of my analysis in, and so I can save it here. Okay, so from here, we can go ahead and copy paste this data into here. These ones are unnecessary, and so then you can Command X and Command V this. And you can organize this data however you want. Although I personally think the most efficient way to export data into an Excel sheet is through a macro. And so I wrote a custom program that allows you to more quickly export data to an Excel sheet. So this is the program that I wrote. And so if you were to run this, you simply go back to plugins, go to macros, hit install, it would pull up a window, and then you can install this macro. And so if I were to run this macro, it would take all the data from the log and put it into an Excel sheet. So keeping an Excel sheet is very useful, but just to quickly note, there are some edits that every individual will have to make to this program that I will attach a download link to. Before use is that you have to rename your sheet name to whatever title you named your spreadsheet. So I think the easiest way is just to copy paste this. If I wanted to copy this name, then I could paste that. Getting rid of this tag, of course, it's just colocalization duplicate. Sorry, this would be this. That's the exact title. And you also need to copy the path name, which is the way the file is stored on your computer. And so on a Mac, this is different for a variety of computers. If you hold the Option key, you can see how the path appears at the bottom here. You can right-click and copy as path name, which copies the location of this file, and you can copy paste that here. Getting rid of these quotation marks here. And what this does is it tells the program where exactly that this value, or where exactly to find the Excel sheet to export the data to. And so let's quickly do this. The Excel sheet does not auto-update because that's just how Excel works, but if you close the spreadsheet and reopen it after running the macro, you will see your data. And so if I were to run this program, you can see that it just extracted the values, these values here. And then if I open the spreadsheet, you should see it put it in a separate sheet because I did not rename sheet 1 into colocalization duplicate. If I renamed sheet 1 into this file name, it would have put it into sheet 1, but instead it created another one. And so you can see it extracted the file name, one of the file names, which is useful in, I will usually go ahead and change the text color for the name of the, or at least the well, like I will maybe put it in red or something. And so when I look at these results, it's very easy for me to see, oh, this is from well 8. And so you can see how it exported all of this data, and you can adjust this however you need to. Like if I wanted to insert a row here, I can add image name, I can add like M1, M2, I can add Pearson's coefficient. I can even add like a separate row that has treatments on it and averages. And so you can do a whole lot with it. This is my current spreadsheet that I work with. And so all of this data was extracted using the macro. I did not have to type any of it. But for my own clarity, I also included the dates I acquired, or the dates the experiment was conducted, as well as the treatment. And then I'm able to extract the data and put it here, and then do averages and build graphs within Excel, which allow me to create my analysis very efficiently. And so using this macro will expedite your process much more efficiently. However, it's up to you. You can, of course, go to the log and just copy paste the data as I showed you earlier and format it however you wish. Just to quickly go over how to install and use the macro. Once you have a log window of any kind, you just have to run the macro itself. This can be done by going through plugins, macros, and install window, which will pull up a file. Once you have downloaded the macro that I wrote, you just have to find it and install it. You will have to do this every time you open Fiji, unless you want to go through the startup window program and insert this macro into there, which I have yet to figure out how to do, but this is also not the most complicated thing. So once you install it, it will appear in this plugins and macros window, and all you have to do is find it and click it. You'll know if it worked if it says it extracted these values. The code is built to provide an error message if anything goes wrong. So if you see something that doesn't make sense, it means that there's an error message. And so from here, you can of course go and find your spreadsheet, and you can see that the data was just extracted in here. I don't want to mix anything up though, so I will go ahead and delete that. If you do increase the space, for example, like I added the tag IF2 here because I wanted to distinguish these two treatments. You only have to add the rows and then add text. So for example, if I wanted to do NSF IF65, just because. Once you add this text, it will auto calibrate and start adding new data where it should be. For example, if I were to run this, let's say if I save this and then run this macro again, you see it worked, extracted it here, and if I were to open this, it'll add underneath the new text that you just created. And so you don't have to worry about creating multiple spreadsheets for your results. You just have to make sure you distinguish where you want it to be, and the program will auto-adapt to send the data where you need it to be. And of course, I can add the data, like I wanted to include my name of experiment and stuff like that. There's a whole lot you can do with this. It's up to however you want to organize it and however you want to label your data.